If we still can't find the programming homework, can we expect that on Thursday? Or?
Okay. What I'll say is we will turn in as many. They have check the grades online and see if we have given you a grade.
Okay.
Okay. If you haven't gotten a grade, then that's where you would probably get nervous. If you can't find a piece of paper, I'm less nervous. Okay. Okay. Let's get started. First of all, any questions about anything logistically? Okay. Some people have asked me about whether or not you can use your, if you haven't used your homework 5 extension, your homework extension yet, can you use it on the last assignment? The answer is yes. Okay. And so, if not, in principle, it's due next class. Yes?
I still can't find my homework 4.
Okay. If you can't find your homework, there are 2 possible cases of can't find homework problems. One is that one more serious than the other. One is if we did not grade your homework. Okay, if it was lost before we graded it versus one that after we graded it. The grades online should be posted, and you should be able to tell if we've got a problem there. And so if you turn something in and you don't see it, that I want to hear about. Okay? If you're telling me that we have a grade and you can't find it in the mess of things, there are a couple of explanations for that, but that I'm going to worry about less. Any questions about that? Yes?
I have a question about the week.
Yes.
How electronically, I assume?
What? How will you get it in? You will get it in a logically week, which means you can turn it in at the final. Okay, so I don't want to see the email, but I do want to see it. If you have your extension, you can turn it in at the final. Okay. Any questions about that? Okay. Again, the final is our next to last class, and then we're going to finish up NP-Completeness today and on Thursday, and then there will be the final. The final will be cumulative. I will say 1 out of the let's say 9-ish, okay, problems will be on NP-Completeness. Okay, 9-ish may mean more, may mean a little bit less. But it's going to be a comprehensive thing with about 1 problem per thing that we've covered. Okay, and so that's how I guess you should study for it. You should look at the homeworks. You should try to go back and figure out what you didn't get before. Any questions? Okay, yes.
So what do you do if it isn't graded?
If it isn't graded, you should send me and the DA's mail. Okay, and then we will do some more serious checking then. Any questions? Okay, so what I'd like to talk about is, again, we're talking about NP-Completeness. I want us to, again, we have to go back. There's one idea here, and that idea is on this slide. And if we see it enough times with enough instantiations of how we're actually going to use this idea, it starts to become, I think, clear what's going on. Our whole idea is that we are going to be developing in here an algorithm. Okay, let me go debunk. An algorithm, okay, for solving a problem called Bandersnatch that works by taking the input to Bandersnatch, translating it to the input of another problem, which we will call mobility. We will use this is a reduction to the mobility problem because we are going to use the mobility problem, the answer of the mobility problem on this translated output as the answer on Bandersnatch of G. Okay? Bandersnatch is assumed to be a decision problem, yes, no. Okay, mobility is assumed to be a decision problem, yes, no. If we do this translation in a careful enough way that it preserves the answer, okay, so that whenever Bandersnatch of G is yes, mobility of Y is yes, we can return the answer of mobility of Y as Bandersnatch of G, and it will be correct. Once we have this algorithm, we have one of 2 different things that it could be used for. If we have a fast mobility solver, okay, and assuming this translation is pretty fast, okay, if we have a fast mobility solver, this would give us a fast algorithm for Bandersnatch. Okay? But if we have a guarantee that Bandersnatch is a hard problem, that there is no fast way of solving it, this algorithm would give you a fast way of solving it if you had a fast mobility solver. And therefore, since there is no fast way to solve this one, there cannot be a fast way to solve mobility, because a fast mobility solver would imply a fast Bandersnatch solver, and that we say is impossible. Any questions about that? Okay, any questions about the basic procedure? How many people sort of get the idea? Okay, what are our candidate Bandersnatch problems? Is Bandersnatch when we're trying to do it? Where do we put the unknown problem? The one we're trying to prove hard. Is that Bandersnatch or mobility? The unknown problem is mobility. What problems can we use as Bandersnatch? Any problem that we know is hard. What problems do we know are hard? Okay. Satisfiability is a possibility. What's another one we know is hard? Yeah?
Vertex cover.
Vertex cover we know is hard because I proved that last class. And maybe we'll take a 3-minute skim of why that was. Okay? Just to incorporate what's going on. And I guess, was there any other hard problems we knew about? Yeah? Click? Well, we don't yet quite know about click. We'll know about click in a few minutes. So yes. Traveling salesman? I didn't really show you traveling salesman is hard. Okay, so I'm reluctant if I'm trying to build up this machinery. But what should be clear is the more hard problems you know about, the better that the better the world is, because we can use any of our known hard problems here. Okay, we just have to know that it's hard. Yes.
Finding a Hamiltonian circuit.
Hamiltonian circuit's another hard problem. I didn't quite show you how to do it. So the other one I showed you how to do was 3-set. Okay? Those are the ones we've shown. Okay? But it should be clear, and this will hopefully be clear today, is that the more problems, once we start getting some problems here, originally there was only one hard problem. The more hard problems we know, the easier and easier it's going to be to do this kind of thing. Because we're going to be trying to do a translation between a Bandersnatch that is most similar to mobility as possible, to make it sort of as easy to do that kind of transformation. Okay? Any questions about that? We're almost there. So the hard part here is really picking how do you do this conversion. And let's just take a very, very fast look at the, notice the vertex cover is hard. Look at that reduction to see what was going on. Okay? In vertex cover, what did we do? We translated a 3-set instance, which had Boolean variables that were either true or false. There were n variables, v1 to vn. And there were clauses, each of which had 3 of them. Okay? 3 elements per clause, each of which was one of these variables possibly complemented. Okay, and you were given an input of a bunch of these clauses. And to do our Bandersnatch to mobility, we had to translate this input into something suitable for a vertex cover problem. Vertex cover decision problem had 2 inputs. One was a graph, and the other was a bound on how big a vertex cover we wanted to look for. Since all the vertices in the graph together would be a cover, finding a cover is not hard. What is hard is finding a small enough cover. Okay, and this is going to the integer is going to define how small is small enough. Any questions? So what was the translation? I went through it last time, but let's just look at what the translation is, because you'll see it's a mechanical thing. In this particular case, I created 2n vertices, where each pair of those vertices represented one of my Boolean variables. And I connected them by these edges. I had these isolated edges. And this was enough to show that any cover required picking one of these or one of those for every one of these so-called gadgets. A gadget's a part of one of these proofs, one of these reductions. So this showed that just to cover the blue edges, that took greater than or equal to n vertices in order to do it. Does everybody see that? Just to cover the blue edges. I also took my M clauses and I constructed M disjoint triangles of vertices, one for each clause. That was 3 times M new vertices. In order to cover just the red edges, I needed at least 2 vertices per clause, right? Per triangle, I have to take at least 2 of these vertices if I want to get all 3 of the red vertices edges covered, right? Any 2 of the vertices would do it. If I don't pick 2 of them, if I don't pick 2 of them, that edge is never going to be covered in any other way. So we knew that just getting the red ones would be greater than or equal to 2 times M vertices. And then I added to it extra edges. Extra edges only makes the covering problem harder, right? There's more work to do, okay? Because you need your set of vertices not only to cover the blue ones, not only to cover the red ones, but also cover the cross ones. And I have added an edge between any variable, maybe this is another one, any variable, so labeled, and its instance in a clause. Those are what these extra edges are. Adding these edges meant that the cover could only get bigger. But what's clever about this design is if there is a satisfying truth assignment to this problem, then the claim is there is a way to cover all the edges in this graph using exactly n plus 2m vertices in your cover. Why is that? Suppose we take a satisfying truth. We need to pick one of each thing. You've either got to pick V1 or V1 prime, V2 or V2 prime. Let's say we picked what happens to be a satisfying assignment, like we did here. If it's really a satisfying assignment, by definition, every one of these clauses has, at least one of those literals in it that we picked. What that means is, out of the 3 connections between this triangle and the variables, at least one of those edges has already been taken care of. Does everybody see that out of this one? In this case, 2 of the edges were already taken care of by variable selection things. Does everybody see that? Actually, all 3 of them. That we got really lucky here, didn't we? Okay? But how many vertices do we still need to take in the clause to cover it? We still need to take 2 of the 3 triangle vertices, or else we can't get those 3 red edges, right? But if all these other edges have already been taken care of, ka-chunk, we can pick any 2 of them, right? In this other one, we have this edge is not taken, this edge is covered. Actually, it turns out this was funny. This was really the one I picked. Okay? Now, if we look at this particular as truth assignment, okay? Because it is satisfying, there is at least one edge to my triangle which is covered by one of the variables that I picked. Does everybody see that? That's what it means to be a satisfying truth assignment. Okay? And once you've knocked out one of those edges, to cover the other connections is easy. Just take the other 2 vertices, and we have got it. Okay? How many people see how this construction is working, what the logic is? A few. How many people don't see it? More. Any questions in particular about what you don't see? Okay? The important thing is that we are doing translation. Let's first think about what we are doing. The key thing is that we translated this problem into an equivalent graph. Okay? So that the same thing is going on in both of them. That's what a translation means. We didn't solve anything in doing that translation. We just reformatted them. What's the difference? What does a Google do when it translates English to Spanish? It comes up with the same meaning, okay, in a different representation. This translation was very, very clever, okay? But note that it preserves, in some sense, the structure of what a SAT problem is. A SAT problem has clauses. A SAT problem has variables. Our graph, in constructing it, preserved that structure. And very cleverly noted that when you have a satisfying truth assignment, that means that you've got in every one of your clauses at least one of the three literals taken care of. That's what it means for a satisfying truth assignment. It means that every clause has something taken care of. Right? And if one of these three connecting edges for every triangle, if at least one of them is taken care of, then it is easy to finish the job with two vertices. It is impossible unless one of the edges is taken care of. Does everybody see that? If you set my budget as I have to use this many vertices in my cover, can't use more. I know you got to pick one out of every pair or else you can't take care of the blue edges. I know you've got to pick two out of every triangle or else you can't take care of the red edges. The real question is there a way to jiggle these things so you also kill the cross edges on the side? And if there was a satisfying truth assignment, then, in fact, there is a way. And that means that if you had a vertex cover of this graph, let's look at this. Here I've got a vertex cover of this graph. Can you read off what the satisfying truth assignment is corresponding to this vertex cover? This is saying V1 is true, V2 is true, V3 is false, and V4 is true. So if you you construct this graph and you feed it to your vertex cover solver, this is the vertex cover it happened to come back with. Note that you get a nice vertex cover of the graph if you want to make a picture for your wall. But the most important thing is that vertex cover tells you what is a setting of those variables such that you know it is in fact satisfying this original SAT problem. Okay? That's what is important about this translation. It translated it in such a way that if I give you the answer to this, I give you the answer to that. Okay? This required a clever translation. This was clever. Okay? But does everybody see how it works? Yes, question.
Here you're translating the 3-SAT into vertex cover?
Here I am translating 3-SAT into vertex cover. To show that vertex cover is hard. Go back again. This always requires going back. It's very complicated. I got to go back to this slide over and over again. What am I trying to do? I am trying to show that because I could translate 3-SAT into vertex cover, okay, that's what I did. I translated 3-SAT into vertex cover such that the vertex cover had a solution on this. Okay, if and only if the original input was satisfiable. Okay? And that way I could use my mobility solver. Yes?
So if there's an edge going to one of the bottom triangles,
Ka-chunk, ka-chunk.
that's the only edge going to the bottom triangle.
Okay, let's go back here and see if we can make this appear. Isn't this kind of cool? Okay, bung. Okay, I guess I've written so much, I guess it isn't so cool even here. Okay, it doesn't like anything magically popped out. Okay, so what is the question now?
If you have an edge going to one of the bottom triangles, it's the only edge going to the bottom triangle. You instead use the other two.
Right. If my proposed cover, let's say my proposed cover was this, my proposed satisfiability thing was this, let me try, let's say this, and this. Let's say I think that's a satisfiable truth cover, truth assignment, right? Well, then when I go back to this thing, this has covered that edge, this has covered this edge is not covered. Any pair of vertices I pick for this triangle will work so long as I pick this. Does everybody agree that this plus either of the other ones, maybe I like this one. And now I've taken care of that clause and all the other edges associated with it, right? And now I go to my other triangle, and I say, well, wait, this edge isn't taken care of because that's not in my assignment. This edge isn't taken care of because it's not in my other assignment. This one isn't in my taken care of. Now I've got to pick two vertices on my triangle to cover the triangle plus those three connections. I can't do it. Does everybody see that? And why can't I do it? It's because this is not a satisfying truth assignment. Okay? That's why I can't do it. If you gave me a satisfying truth assignment, now suddenly there is an edge taken care of here, and now I can finish the job, right? Now I can go ka-chunk. Okay? So the problem of finding if your mobility solver, your vertex solver, takes this graph and finds a small vertex cover, then mobility is really solving my SAT problem and saying, yes, there's a satisfying solution. I can just read it off from what you gave me. But if not, I can't. Any questions about that? Yes?
So can you explain how do you construct that triangle? Because there's no repo.
Okay, so now what you're saying is, how did I construct those triangles? Okay? The first thing to note here is that these triangles are the clauses of my input. Do you agree that this was my input SAT problem? This was my input SAT problem that you gave me to translate, right? So because I translated it, I constructed this thing. Okay? Does everybody see that the translation is a mechanical thing that I'm doing?
It's kind of random.
It's arbitrary input, not random input. Whatever you give me, I translate it. It's like Google's translator from English to Spanish. You type in anything, it's going to give you Spanish, right? But in order to do this, I had to describe an algorithm that took as input the set of clauses and as output built the graph. Which, if you understand my construction, this is a really easy transformation. Okay? It's clear you could write a program to do this. Okay? Designing the program to do this is what took smarts. And it was a very clever design because it preserved the correctness of this. Any questions? Any more questions about what we were doing here? How many people sort of see it? How many people don't see it? Okay? Okay. Now, coming up with that transformation was very, very clever. Okay? But now that we start getting more and more NP-complete problems that we know are hard, proven hard by clever people, the tools are now become more useful for people who are less clever. Okay? And in particular, if we can start from the right problem, a problem that is that we know is hard, that sort of smells like the problem that we're interested in. Sometimes the translation isn't so hard, okay? And again, on the final and on the homework, I'm not going to ask you to do a crazy hard transformation. Let's look at some simpler ones, okay? Now that we have vertex cover under our belt, this is where you should start to get hopeful, okay? One famous problem that we can prove hard from this is something called maximum clique. What is a clique? Well, a clique or a clique in your friendship graph are a bunch of people who know each other. Every one of you know each other. It's like a gang, okay? So suppose this was a Facebook graph. What is the biggest gang in that represented in that part of the Facebook graph? It should be clear that there's a set of 5 hoodlums here, all of whom know each other. Does everybody see this? Every pair of people in the gang know each other. Okay? And that is what we mean by a clique. A clique is a set of vertices such that every pair of these vertices is an edge in the graph. Okay? Any questions about what a clique is? Can anybody give me an algorithm, given any graph, to find a clique in it? Not necessarily a big one. Okay? Can anybody give me an algorithm to find, given a graph, try to find a clique in it? A set of vertices, yeah?
If there's any edge in the graph, there's a clique.
Does everybody agree that, look here, Ma, here is a clique of 2 people. Okay, it's a gang. It's like Bonnie and Clyde, I guess, is a gang, right? Okay? Finding a clique, a complete subgraph, is not hard, right? Testing if the whole graph is a gang, meaning it's complete, is not hard. Just check every pair of edges and seeing if it's there. But finding if the graph contains a large clique, okay, turns out to be very hard. Okay? So the question we want to solve, given a section of the Facebook graph, what is the biggest group of people that all pairwise know each other? Okay? That is the clique problem. Any questions about that? Okay? How would we show that this is hard? Is this clique going to be Bandersnatch or mobility? Okay, yeah?
It's mobility.
It's mobility. What Bandersnatch do we have that is closest to it?
Probably vertex cover.
Vertex cover. Why does vertex cover smell like, like clique?
I picked it because it's a graph problem.
They're both graph problems. Is there anything deeper about them? Are they just graph problems? They're both looking for subsets of vertices, okay? So there is something like this. You're looking, trying to do something that looks similar here. Are you trying to pick big sets of vertices or small sets of vertices? Well, vertex cover, you want to pick a small set of vertices, okay? Clique, you want to pick a big set of vertices, right? So we're seeing similarities but differences, right? And we got to factor that into doing our translation. Okay? Any questions about that? We're going to do this by 2 very simple transformations. Along the way, picking up an extra NP-complete problem. There is first an observation that is interesting about vertex cover. What if I take the vertices in my vertex cover, okay, and take the vertices that are not in my vertex cover? Here I have a graph. The square things are, the square things, or now the red things, are my vertex cover. Does everybody see that every edge in the graph kisses one of the red ones? Possibly 2 of the red ones. Okay? What is interesting about the edge, about the red, the black vertices, the vertices that are not in my cover? Okay? Is there any edge between 2 blue vertices? Let's look at this. Looks like there's no edge between any two of the the vertices that are not in the cover, right? Why is that? Think about this for a second. If we have the red vertices form a vertex cover, what about the rest of the vertices? Can there be any edge between two of the non-cover vertices? Yeah?
No, because that edge wouldn't be covered.
No, because you were telling me the red ones made a vertex cover. That means that every edge has to have at least one endpoint on a cover vertex, right? Suppose there was an edge between two vertices that were not in the cover. What does that say about your cover? Yeah? Your cover is naked. It doesn't cover, basically, right? Does everybody see that? Okay? So what does this mean? This seems like how many people see that observation? The non-cover vertices, okay, have no edges between them. And in particular, they form something we call an independent set. What is an independent set? If we go back here, I can maybe go back. Kabunk. Okay? An independent set is a collection of vertices where there are no edges between them. Okay? What I claim this means is the following. Finding a large vertex cover is exactly the same thing as finding a small vertex cover is the same as finding a large independent set. Let's think about that for a second. Let's consider the maximum independent set problem. Independent set problem is I give you a graph and I give you a bound K. And I ask, does there exist K vertices in G with no edges between them? Okay? I claim that this maximum independent set problem, okay, is very closely related to vertex cover. In particular, could you show me how to use given vertex cover? Could you show me how to solve, vertex cover is my known hard problem. Given a graph G, could you show me how to solve vertex cover if I had a fast way to find the maximum independent, G and some bounds K, right? Can you show me how I can do that? Okay, if I had a way to solve independent set on a graph H with J vertices, could you find that there is a way to tell me if there is an independent set of J vertices in H, that's the same question as if you can find an a vertex cover of K vertices in G? Okay, yeah?
You just take H minus the maximum independent set to get the vertex cover, the small vertex cover.
So I think what you're saying is if I say H equals G, same graph. If I say J is equal to N minus K, let's look at this thing. What this is saying here is what? The graph G has a vertex cover of size K if and only if the graph H has an independent size of N minus K. Okay? Think about this. This is one you got to understand. Okay? And so let's focus on this one for a second. Okay? If we have a graph, here is our graph. And it's got edges. Ka-chunk, 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 ka-chunk. If I find a vertex cover of this graph, what's a vertex cover of this graph? There's one. There's one. I think that is a vertex cover of this graph. Does everybody see it? This vertex cover of size 3 gives me an independent set of size 7 minus 3, or 4. Does everybody see that, again here, this, and this is an independent set? The graph G has an independent set of size K if and only if the graph G the graph G has a vertex cover of size K if and only if the graph G has an independent set of size n minus K. And so, you could use the independent set solver to solve vertex cover. Okay? How many people see why this is what I've done here? Bunch of people in the front row. How many other people? Any questions about it? Like, I don't see it is a good question. Okay? Yeah, question.
I don't see how exactly it compares to the click.
Okay, I haven't talked about click yet. We're talking about independent set and vertex cover. I'm going to give you a bonus NP-complete problem out of the whole deal. Okay, and that's going to be independent set. Okay? Does everybody see that asking, gee, I want to find an independent, a vertex cover of size K, is the exact same question of finding an independent set of size n minus K? How many people see that? Okay, how many people don't see it? Okay, that is exactly what I have written down here. Does everybody see I have transformed it? This was so simple, my transformation is I'm using the exact same graph, really. Okay? And all I've done is change the size. Okay? This is all I needed to do to prove that independent set is NP-complete. Okay? Any questions about that? This is the kind of thing I want you to be able to do on an exam. Okay? I don't want you to go do these very, very fancy constructions, although they're beautiful. They take practice, and that I realize is hard. But you see here that this is a perfectly understandable transformation. Any questions? Okay? Any questions? But I wanted clique, okay? How do I prove clique is NP-complete? Okay? What are my possible, and now I want to do Bandersnatch mobility, which is going to be clique? Is clique going to be Bandersnatch or is clique going to be mobility? Clique is going to be mobility. Which of my possible Bandersnatches smells most like finding a complete graph? Okay? I could use set. I could use 3-set. I could use vertex cover. I could use independent set. Which one smells most like clique? Yeah? Independent set. Why does it smell like that?
Well, because the independent set are vertices that there's no edges between them. So you want to find the ones.
What's the similarity between a clique and an independent set? Ka-chunk, ka-chunk, ka-chunk. That is a clique. This is an independent set. Where there were a lot of edges, it was an edge, now there is not an edge. Does everybody see that? Both cases now, we want large subsets of vertices. One that has as many edges as possible, one that has as few edges as possible. Does everybody see that? So let's think about it. What did we say our Bandersnatch was going to be? He says independent set. Independent set takes a G and a constant size, right? We want to now find, is there a clique in some graph H of size J? What is our graph going to be? Okay? We'd like to do it so whenever there was an edge in the other graph, the difference between this and this is wherever there was an edge, we take it out, and wherever there isn't one, we take it in. What's the name of that operation on a graph? Yeah?
It's the graph complement.
Graph complement. Does everybody see that? Suppose I take my graph H and I complement G. Again, nice graph. Okay? Now, how big a clique in my complemented graph will correspond to an independent set of size K? How big a clique in my complemented graph will correspond to a clique of size K in the original graph? Okay, nobody's saying anything, so I'm going to ask again. I've now complemented my graph. How big a clique in graph H, okay, corresponds to an independent set in G of size K? K. Does everybody see it? Now, what is this reduction saying? I am going to transform my independent set problem. And a given graph G with K, K is my bound. I'm going to transform it by complementing the graph. That's a mechanical transformation, right? It's easy to write a graph complement subroutine. And then ask in my new graph, is there a clique of size K? If there is a clique of size K in this graph, then that meant that in the original G, those exact same vertices would have had an independent set. So is it any harder to find the clique of size K in the complemented graph than it is to find an independent set of size K in the original graph? No, they're the exact same problem. Once you have this transformation, now we see that if we had a fast clique solver, we've got a fast independent set solver. But if we had a fast independent set solver, that would have given us a fast vertex cover solver. And if we had a fast vertex cover solver, we would have a fast set solver. But there's no fast set solver. So there's no fast vertex cover solver. So there's no fast independent set solver. So there is no fast clique solver. Okay? Any questions about that? Yes?
Yes. On the exam, are we allowed to use any algorithm we want as long as we know it's
Okay, on the exam kind of questions, I will give you one of two things. I will either tell you what I want you to use as Bandersnatch, or you're free to use anything that you know about. Okay? So, part of the job is to find which is the best one. That's a large part of the game here. Which problem smells most like the one you care about? Any questions about that? Okay? Any questions about why we have just proven that clique is hard and vertex cover and independent set are both hard? Any questions about that? I'd like to see that again is a good question. These are the stature of things that I'd like to think you're capable of doing, okay, if you practice on. Any questions about it? Okay? Any more questions here? Okay. Let me confuse you for a minute, just for a second. What is it? Did we ever talk about the independent set problem in here? Let me now confuse you. Make sure you get this down before I confuse you. Okay? Did we ever talk about independent set in this class? Yeah?
No, we've only been talking about independent set decision problems.
Well, okay. Now, I'm not trying to get you. I mean, the independent set problem. Is there any time in this semester when I talked about the independent set problem? We tried to solve it. Okay, I claim there was a time we tried to solve it. It was way back the first day of class. Does anybody remember the movie star scheduling problem? Okay, what was the movie star scheduling problem? Okay, yeah?
movie star scheduling problem was you had a set of movies taking place over a specific amount of time. You had to see how what is the greatest number of movies.
Right. So the question was, I gave you, there was a certain period of time over which every movie project took place. Your goal was to find what was the largest set of movie projects that you could take, such that no two interfered with each other. Does everybody agree that we could have made this an independent set problem? Right? Where the vertices correspond to movies. Okay? There is an edge between any pair of movies. Okay? That overlap. Does everybody see that? Okay? Then what do I want? I want the largest number of movies I can pick up, such that there is no overlap between any two movies.
Hold on a minute, though.
Okay, wait, first does everybody see how many people remember that problem and agree that this can be seen as an independent set problem? Okay, if not, I'll go through that. How many people want me to explain again why this looks like an independent set problem? Okay, why is it? Recognize that here I've got movies. In this case, we'll call this movie A, B, C, D, E. Here are vertices A, B, C, D, E. Does everybody see that? What edges are there in this graph of things that overlap each other? A overlaps B, right? A overlaps C. B overlaps C, right? D overlaps C. Okay, D overlaps E, C overlaps E, right? Are these all the edges in the graph? What is the independent set that we took? Either A or B, okay? Those vertices are an independent set in this graph. Okay? Does everybody see that? Okay? So this is an example of where an independent set problem comes up. Okay? Any questions? Now you've got a thing you're concerned about, yeah?
Yeah. Didn't you just transform an unknown problem into a hard problem? Isn't that backwards?
Now doesn't everybody see that what I did here is he's kind of got me here. Okay? What I did was I took a problem which seemingly is an unknown, is a version of, is a one problem, and I translated it into a hard problem. Okay? And I then said, now you can't solve the independent set problem, the movie star scheduling problem, I would have been committing a sin for just this reason. Right? Does everybody see that? In fact, what this kind of shows is not all instances of independent set are hard. The set of graphs you get from this sort of movie star scheduling problem, those in fact can be solved easily. But there are harder versions of independent set that in fact are hard to do. Okay? Any questions about that? If you didn't get what I just said, forget about it. That's a little bit of a digression, unless anybody wants to question about it. Okay? Any questions? Okay, let's get back into but what is important? Independent set, you see why an independent set type thing comes up? I tell you in general it's hard. Okay. Let's now go to the problem of the day. I'm finally ready to, I think, deal with the problem of the day. What is the problem of the day? The problem of the day says, view, full size, kabunk. We want to solve something called the dense subgraph problem. What is the dense subgraph problem? I give you a graph G, and I want to find integers k and y. And I want to find out, does this graph have a subgraph of exactly k vertices with at least y edges on it? Okay? See what I'm giving you now? I'm giving you a graph, and I'm saying, true or false, does there exist a set of k vertices in this graph that between those k vertices have at least y edges defined between them? Okay? That's what the densest subgraph problem is. Can we prove that densest subgraph is hard? Okay. What would be densest subgraph? Is that Bandersnatch or Bobilly? Bobilly. We want to solve densest subgraph of some graph H, K, Y. What known NP-complete problem smells most like densest subgraph? Okay. I hear, yeah? You're saying vertex cover, he's saying clique. Now on one level they're the same, and so in some sense it's an academic discussion. Except that there's a lot more work to translate from one than the other. Which one of these problems smells most like densest subgraph? We'll put it to a vote. Okay? Why? Well, maybe we'll ask a question. Why do you think it's vertex cover?
Because you could do the subgraph. You could just have all of the edges be y.
Okay.
That would be the graph with all of the edges you're asking.
All the edges that you're asking, type of thing. Why do you say it's clique?
I say it's clique because we're talking about a subgraph in the graph, and it has a lot of edges and exactly so many vertices.
Okay. Which argument do you guys find more compelling? Let's think about this. Which problem sounds more like densest subgraph? Is it clique or is it vertex cover? Who here says vertex cover? Who here says clique? See, a lot of people like clique. To me, I see why. Okay? Because again, a clique is a dense subgraph. Okay? A vertex cover is not, the graph doesn't have to be dense or not. In fact, so I don't, there's a connection, but I don't see it. But I do see clique. Let's say clique is G, and let's say some bound, let's call it C is the size of my clique. How would I transform that clique problem into densest subgraph? I need to show what H is equal to, I need to show what K is equal to, and I need to show what Y is equal to. Right? And then I've done my transformation. So what should my graph that I'm solving densest subgraph on be? You want to say it's the same as the graph. Okay, that might be true when we see the whole thing. How many vertices do we want to look for? C. And how many edges do we want to look for? Does everybody see here? This is C choose 2. Okay? What is this saying? That a clique, remember, was K vertices, all pairs of which are there, right? If we have a clique on K vertices, how many edges are going to be defined between them? All pairs or K choose 2. Does everybody see that? Asking whether there are a set of K vertices which have K choose 2 edges between them is exactly the same thing as saying, is there a clique on K vertices? Okay, how many people see that? See why this is a correct transformation? Okay? The clique problem is just a special case of densest subgraph. Okay? And so yes, if you've got a densest subgraph solver, by calling it with these parameters, you can turn it into a clique solver. But clique is hard. You can't solve it fast. So there can't be a fast solution to densest subgraph either. That's what this is saying. Okay? Yes?
Can you explain why it's C choose 2?
Why is it C choose 2? We have to try to convince our densest subgraph solver to find what we're looking for. After all, it's dense, okay? We have to convince it, okay? So how do we tell it, find me K vertices that are a clique? Okay? What does it mean for K vertices to be a clique? What does it mean for a set of vertices to be a clique? With every possible pair of vertices has an edge. And what's another way of saying that? It's saying that if your K vertices have a total of K choose 2 edges defined between them, right? Isn't that just another way of saying the same thing? What is that Google Spanish-English translator doing? It's trying to find another way to say what you're trying to say, right? This time say it in Spanish, okay? But that's what you're trying to do in these transformations, is to change a problem into an equivalent way. Bang it into the language of the other problem. Okay? Any questions about this? This is the kind of thing I'd like you to be able to do. Okay? Any questions about that? Okay? How many people see why this proves the densest subgraph is a hard problem? How many people see it? How many people don't see it? Okay? And want to see it? Nobody. Okay? Any questions about that? Okay? If you've got the right starting point and the right way to look at this thing, these transformations are not that hard. They fall out of a certain logic of what is the problem and what is the thing that looks most similar to it. Any questions about that? Okay? Any questions? Okay. Unless there's any more questions about this one, I'm going to give you another hard transformation just to sort of see how magical these things can be. Okay, but any questions about the simple one? Any questions? Kabunk, kabunk. Let's look at another problem, okay, called integer subset sum. Okay, it's sort of like it's a variation of the knapsack problem, which I think we talked about the knapsack problem in here at some point, right? What was the knapsack problem? I gave you as input a set of numbers, and I gave you a target problem, a target, and I asked, is there a subset of these numbers such that when you add them up, you hit the target, right? Does everybody see what the problem is? You are a thief. You have the ability to carry out this much weight, okay? Let's say in gold. You have gold pieces of this much. The size of the pieces given here. You want to find out, is there a subset of these items I can steal that I can fill up my knapsack perfectly? If I put in too much, the knapsack rips and I get nothing. It doesn't pay to be greedy, right? If I don't fill up the knapsack, it's a lost opportunity, okay? But not for all, it may not be possible to fill up my knapsack. Here I claim, if you take this element, this element, this element, this element, this element, this element, and this element, that will add up exactly to that. Okay? The subset sum problem is given your collection of integers and given a target. Figure out which integers add up to that. Okay? Any questions about what the problem? How many people understand the problem? See why it comes up? See why you might want to solve it? Okay? Any questions about that? Okay? Now, let's see if there is now this problem isn't look at all like any of the other NP-complete problems we've had, right? Is this a logic problem? Like SAT? It is not a logic problem like SAT. Is this a graph problem? I don't see where the graph is, right? So this one may look weird. I mean, if I want a starting point, which problem looks most closely like this problem? Okay, you're gonna, yeah?
What about like the movie scheduling problem?
You say the movie scheduling problem, where there again, that's also about, I guess, somebody trying to get a lot of money. So both of them, the movie scheduling problem and this one are both about someone getting a lot of money. That's a way that they're similar. Now, a bad problem is the movie star scheduling problem is not NP-complete. So that's a bad place to start from, okay? But that is a numerical thing, okay, sort of, maybe, kind of, okay? And anybody of which problem smells like this one? Okay? It should be clear that a lot of the ones that are the graph ones are about picking subsets of things, right? Vertex cover was about picking subsets of vertices, right? Here we're looking for subsets of numbers, okay? Let me show you a transformation of how you would convert vertex cover to subset sum. Okay, it's kind of an amazing thing. what are we going to do? We're going to start from taking our graph and representing it by an incidence matrix. You may remember the incidence matrix from a not particularly beloved daily problem we went through earlier, right? What was the incidence matrix? The rows were vertices. The columns of the matrix are edges, okay? And there is a 1 if and only if the edge is incident upon that vertex. Does everybody see this? Here we have got edge 3 is between vertex 0 and vertex 1. Does everybody see that? That's what it means. Edge 4 is between vertex 2 and vertex 3. Does everybody see what I mean by an incidence matrix? Okay? We talked about it when we had the daily problem. Okay? The incidence matrix is a way of representing the graph. That much should be clear. We've got all the vertices listed, and for every edge we know what the 2 endpoints are. So it should be clear, an incidence matrix is a representation of a graph. How many people see that and are agreeing with that? This should be obvious. Okay, any questions? Now, note that if we think about it, what does a row of an incidence matrix look like? Okay, does that look like anything? Yeah?
It looks like the degree of the vertex.
It looks like the degree. The number of ones is the degree of the vertex. But what does that row look like? Bits in a
bit array.
A bit array, or you might say a number. Could you view this as a binary-like number? Okay, now number. Now we're starting to see maybe a connection here, right? I am going to convert each one of these rows into a number. Now this is going to involve cleverness, so it's not something that you're supposed to say, oh, why didn't I think of that? Okay? But you're supposed to say, yeah, I see what the guy's doing. Okay? What are we going to do? We are going to notice here, there's some interesting properties of this incidence matrix. You said that the number of ones, you just said, a number of ones in every row is equal to the degree of that vertex. That we agree. What is the number of ones in each column? How many ones are there in each column in an incidence matrix? Okay, 2. Does everybody see that? That's by definition, because every edge has 2 endpoints, right? So what are we going to do with this? What I am going to do is, I am going to do a reduction from vertex cover. And in vertex cover, what is my vertex cover thing? In vertex cover, my thing, I've got a graph G, and I've got a bound K. Does everybody see that? That's for vertex cover. In my subset sum, I've got a set of n integers, right? And I've got a target, right? This is sort of like this a little bit, right? Does everybody see that the target is what you're trying to hit in the subset sum? The size of your cover is the goal of what you're trying to hit in getting a vertex cover, right? So there's maybe a little bit of an analogy there. I don't want to overstate that. Okay? But what am I going to do? Here I have a graph on n vertices and m edges, right? I am going to construct n plus m integers out of it, out of this incidence matrix. The first set of m integers, 1 for every edge, is simply going to be representing by that integer standing with just a 1 in the appropriate bit. Okay? So this is going to be one of my integers. This is going to be another one of my integers. 1, 2, 3. These are going to be 5 integers I will have created each one corresponding to an edge here, right? I am also going to create one integer for every row of this matrix. Okay, does everybody see that? Okay. What is interesting about this? So now I've got here, there are n vertices, there are m edges, right? I'm going to create n vertices, n integers corresponding each to the rows, and m edges, integers, each corresponding to the columns. These are my column ones, these are my row ones. Okay? What's interesting about this? Suppose I have a vertex cover. What is a vertex cover of this graph? Can someone tell me about what a vertex... Where's a vertex cover of this graph? Is that a vertex cover of that graph? What do I get when I add up the numbers corresponding to those two integers? That would be 0, 1, 1, 1, 1, and 1, 0, 1, 0, 0. What if I add them up? Okay. Well, what should be clear, actually, what am I trying to suggest? If I add it up, note that if this is a vertex cover, at least one 1 has to be in every bit position before I add it. Does that make sense? If this was a vertex cover, because it's a vertex cover, it has to represent, okay, it has to be at least 1 1 associated with each one of the things that we're adding. Okay? Let me say that again, because that I may have been a little sloppy about. Okay? If we take a look at these things, note that if these vertices form a cover, then that means that there is at least 1 1 in every single column. That is what a cover means, right? Adding it up somehow means accumulating those things, right? So there's sort of a connection here, okay? Any questions so far with the intuition? Maybe it's not yet clear. Let me now describe exactly what these integers are, okay? And then I think it'll maybe become more obvious. These integers, it turns out, are going to be written in base 4. Not binary, but base 4. What are these integers? Well, I'm going to interpret them as base 4 numbers, and there's going to be edge numbers corresponding to 4 to the I, meaning 4 to the 1, or, 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3. Does everybody see that in base 4 numbers, this number is the same as 0, this number is, actually no, this number is nothing. If we interpret these numbers as base 4 numbers, this is what? This is the number 4. Does everybody agree? This is the number 16. This is the number 64. This is, I think, the number 256. Okay? These are going to be my edge numbers. Okay? My vertex numbers were going to be the row of the incidence matrix where I stick an extra 1 in the high order bit. Okay? So this number here, if this was my row of my matrix, this was 4 to the 0 plus 4 to the 1 plus 4 to the 2 plus 4 to the 3 plus 4 to the 4 plus I'm going to stick a 1 as the extra high order bit. Okay? I say bit even though it's a base 4 number. And my target number is going to be 2's in every digit except for the most significant digit, which is going to be k, my vertex cover size. So what does this mean? My target here is going to be 2, 2, 2, 2, 2, written the number of edges times, preceded by k, the constant in my vertex cover. Okay? And I'm going to ask myself, is there a way to take the vertex cover numbers, the vertex numbers, and the edge numbers, and have them add up to exactly this? Okay? What is interesting here? Okay? Suppose I have a vertex cover of size k. What does that mean? That means that there are a set of k row vertices with the property that when you take these things down, the union of these things is going to cover every single edge. Right? Isn't that what a vertex cover means? What do we get if we take the vertices, the numbers corresponding to the vertices in a vertex cover, and add them up? What did we get? That was the same as adding up, we said, I guess in this particular case, this row, what was a vertex cover? This, let's say we took this cover, this vertex cover. If we added this up, plus this, what do we get? Okay? If they are base 4 numbers, this is going to be 1 plus 0, it's going to be 1, right? This is going to be 1 plus 1, it's going to be 2. This is 1 plus 1, it's going to be 1. This is 1 plus 1, 0, it's going to be 1. 1 plus 1, it's going to be 1. If this had a higher order number to it, like I said, that's going to give a value of 2 here, because we're adding 2 of those things, right? Does everybody see that a collection of k vertices, which add up, which are a vertex cover, if you add up the rows, you're going to be getting a bunch of numbers, each of which is, okay, going to be either, if it's a cover, the sum here in each digit is going to be either 1 or 2. It can't be 0, because then you didn't have a cover. Okay? How many people are with me a little bit? Only half arms up at best. Okay? But what do we see what a cover looks like? What is a cover? A cover is a set of vertices such that every edge is taken care of. Right? Here we've got a set of vertices such that each edge is taken care of. What that means is, if we added these numbers up, every digit field has to be at least 1, because it's a cover. That meant that the bit, that the edge, since the bits that are on here correspond to the edges incident upon that vertex, right? By picking this vertex, I get credit for the edges that I kiss, that I'm incident upon. Okay? And the union of these things, okay? If in fact you give me a cover, if I add up these 2 numbers, I am never going to have a 0 field. A 0 field would mean that the edge was not covered, not touched by at least one of the integers I added up. Okay? That's what the connection is between the adding up of these numbers and the vertex cover. Any questions about it? Okay. I know no questions, but I know because there's not enough light going on. Why did I say these are base 4 numbers? What does base 4 mean? If I add up all the columns over here, what number do I get? If I add up all the bits in a column, how much do I get? 2. That means that there's never going to be a carry over to the next digit if this is a base 4 number. Does everybody see what I mean? If it was a binary number, what is 1 plus 1 in binary? Well, 10, which means that that digit would be a 0, right? And carries mess this thing up. If I write these numbers as base 4, or base 10 if you're happier with base 10, okay, you're never going to get a carryover. If my goal is to get a k followed by a bunch of 2's, what's the only way I can do it? Well, if you give me a vertex cover, when I add those numbers up, I'm going to have at least a 1 in every digit, and possibly a 2, right? What else can I add to get that 1 into a 2? I could add up this number. Okay? Actually, let's just get rid of this thing here. Okay? Does everybody see that if I took this number here, adding this 1 number here, corresponding to that edge, by adding this to my total, I would convert that 1 to a 2. By adding this, which one to this? This was not going to be this, not going to be that, not going to be that. By adding this number, I believe the number I want is this one now. Okay? I would convert that 1 to a 2. Okay? Because this is base 4 numbers, I can't add enough of these things so that any digit carries over. Does everybody see this? There's never more than 3 bits in any column if I added all the numbers together. If I add all the numbers together, what am I going to get? I am going to get n followed by 3, 3, 3, 3, 3, 3, 3. If I want to add it up so that it's equal to k followed by 2, 2, 2, 2, 2, 2, 2, the numbers you need to pick are k of these guys, exactly k of these guys, such that when you union them, you get at least one of the 1's in each edge. Okay? And if you need a second one, you pick up some of these guys to finish it up. Okay? Any questions about this? The details, I can see where you're getting lost. But do you see that there is sort of a little bit of a sense in which these problems start to look the same? And if you follow my construction right, what I just did was the following. I have shown you how to solve vertex cover by translating that into a set of numbers, s, and a target integer, such that subset sum on t and s is going to return the exact answer as vertex cover of g on k. Okay? Any questions about it? This is a complicated reduction. You don't have to do it. Okay? I'm not expecting you to find that. Yes?
For this particular problem, what does each vertex actually represent compared to n?
Each vertex is being translated into a number. I am going to be converting each vertex into a number and converting each edge into a number, with the very careful property and a target number corresponding to what my problem was, with the very thing that if you find a subset that adds up to the target, you have solved vertex cover. Okay, let me just see where we are before we go. This looked hard and is crazy, and you're saying, my God, how would anyone come up with this kind of thing? Next class, we are going to do my annual NP-Completeness Challenge. What is the NP-Completeness Challenge? I am going to let you pick from a large list of problems that are known to be NP-complete by somebody in a research paper. And I'm going to try to prove that problem hard, standing up here, doing this Bandersnatch Bo-Billy thing. Because once you understand the logic here, it is not as complicated as it sounds. It requires some cleverness, but it's really not as bad as you think. For now, learn how to do the simple ones, the daily problems, okay? And next class we'll see how you come up with hard ones if you try. Thanks for your attention.